Okay, so the balanced equation for the combustion of methane. Methane we should know is a 1-carbon alkane because of the ane. If we follow the general formula, we should get CH4. And we should know that combustion involves a reaction with O2 to make CO2 and water. To balance it, we end up with 2 oxygens and 2 water molecules. Okay. Now, in order to solve these bond enthalpy questions, we have to draw out all of the reactants. Now, oxygen actually has a double bond. And because there's 2 of them, I'm going to draw that one twice. So these are the 2 reactants. And then they turn into CO2 and 2 water molecules. Now I'm going really fast, but that's because I'm assuming you've stopped the previous video to try it. We've also drawn these ones a couple times when we were working on balancing equations and things like that. So now I've drawn it out, and now I need to figure out what bonds are being broken and what bonds are being formed. So I have to break apart all of the atoms in the reactants. So I'm going to break all of these bonds. So all of those are C to H bonds. And I have 4 of them to break. So 4 times C to H. I also have both of these bonds to break. So I have 2 times O to O double. Okay, let's find those values. Well, previously I found C to H was 414. So 4 times 414. Now I have to find O to O. O to O is 498. So 2 times 498. Remember, over here is where I find the double and the triple bonds. Okay, on the right-hand side, I've got a C to O double bond and another C to O double bond. So I've got 2 of those. Now I've got to find the C to O double bond. That is 804. So I've got 2 times C to O, 2 times 804. Now I have to count the bonds between O and H. They're all single bonds, and there's 4 of them. 1, 2, 3, 4. So it's going to be 4 times that O to H bond. Where is O to H? Well, I have to go look in this table again. So here's H, or here's H, it doesn't matter. If I use the one here, I'm going to go across till I get to where O is, and I get 463. If I use this H, I'll find the same value if I go to where O is. So it's listed twice. So it's 4 times 463. Okay, now we've got to do some quick math. Get your calculators handy. 4 times 414, we get 1656. 2 times 498, we get 996. So the energy in, if I add those 2 values together, is 2,652. So I have to put that much energy in to break all the bonds. That's the energy up. Okay, energy out. Well, 2 times 804 is 1608, and 4 times 463 is 1852, and if I add those together, I get 3,460. Well, this is the energy release, so this is the one that we subtract. That's the one where the energy is leaving the system, so the arrow comes down. If I find the difference, so if I do 2,652 minus 3,460, I get that the change is minus 808. So the change in enthalpy, the change in energy for this reaction is negative 808 kilojoules. The negative sign tells me that it's being released or lost from the system. Where does that energy go if it's lost? Well, if it's lost, it exits. It goes to the surroundings. So this is an exothermic reaction, and it releases a lot of energy. So this is combustion, the whole focus of our unit about fossil fuels and burning fossil fuels. And so now we can calculate that for every mole of methane, every methane that we burn, we're going to get out 808 kilojoules of energy to the surroundings. So it's going to make those surroundings very, very hot. And that is a very useful thing about methane and the other fossil fuels.